Well, we usually start a couple minutes after the hour, it being MIT, so I'm going to give people just a minute or two to trickle in here. But first of all, thanks to everybody for being here bright and early on a Monday. I know that it's not everyone's favorite time for a meeting, but this is what fit the schedule, so here we are. We have the whole thesis committee is here with us now. They are myself, Professor Meyerson, Professor Powell, Professor Winter. We have a few other folks from the department here, a number of students and friends. And so it looks like a group. See, I waited a couple of minutes, now it's 56 people. The numbers just rise, so. Well, I had another big shock yesterday. My daughter revealed that there is a boy. So now I have to figure out who is this boy.
I can't help you there.
No. I understand he's a course 2 graduate, so that's a good sign. All right, it looks like we're up to 68 people here, and we're a few minutes after the hour, so I'm going to go ahead and get us going. First of all, thank you everyone for joining us this morning for the PhD thesis defense of Quantum Wei, who is in the Department of Mechanical Engineering at MIT and a member of my group. Quantum did his bachelor's thesis at MIT in course 2, finishing in 2015. He completed his master's thesis at MIT in 2017, where he worked on energy savings and 2-stage reverse osmosis. Now for his PhD work, he's going to talk about improving the performance of batch reverse osmosis. Quantum has been involved in a wide range of activities around MIT as well. He was co-president of the MIT Water Club from 2017 to 2018 and co-vice president the year before that. He helped to revamp MIT Water Night, resulting in record-breaking attendance. More than 400 people attended. He has been a graduate resident advisor since 2019, and he's also been tutoring English through the MIT ESL program for service employees. He is the co-founder of Harmony Desal, a company that's aiming for efficient batch RO. Harmony Desal has won the MIT Clean Energy Prize, 2nd place, the MIT Water Innovation Prize, 3rd place, was a finalist in the MIT 100K competition, and also Northeastern runner-up in the 2020 Clean Tech Open cohort. He will be working, or has been working, on another project called Project Restore Us, which aims to build a more equitable food system in partnership with local restaurants. In 1 year, this project has raised $500,000 and delivered 500,000 pounds of groceries to food insecure households in the Boston and Cambridge area. And in the summer of 2021, he will be in Delta V, the MIT Startup Accelerator, in connection with this. On the research side, Quantum has published 7 journal papers, published or in draft. He has been issued 1 US patent and has 1 patent application pending for RO-related inventions. He has done 6 conference presentations. These include one at the University Council of Water Research in 2016, where he got the Best Student Paper Award for stage reverse osmosis, and another at the 2019 Membrane Technology Conference and Exhibition, where he got the Best Student Paper Award for batch reverse osmosis. So I think at this point, I've given you some idea who Quantum is and the range of things he's done. And I will now let Quantum tell you about his PhD research. Quantum, over to you.
Thank you, Professor. Thank you, everyone, for coming today. I really appreciate it, and I'll dive right into it. Over the past 4 years, the question I've been investigating is, can batch reverse osmosis make desalination more affordable and sustainable? And the answer is, yes, it can. So we can all go now. But seriously, just a week ago, I might have said yes to that question, but not as confidently as today. I believe that batch RO will make water desalination more affordable and sustainable, but for a different reason than the one that I've been thinking in my head for basically the entire PhD. But we'll get to that. But first, why do we care about desalination? Well, by 2050, it's projected that 6 billion people will face freshwater scarcity problems. This is due to 2 reasons. One, as populations grow larger and wealthier, they consume more and more water. So there's a growing demand. At the same time, due to the effects of climate change, rainfall patterns are becoming more extreme and more uncertain. So the supply is becoming more unreliable, and you can expect to see more and more dry reservoirs like this one, more and more drought. This is the Earth's fresh water. 2/3 of it is frozen in the ice cap, so it's not really accessible to us. The remaining third, that is our fresh water supply. Pretty much all of our drinking water comes from that third. And that fresh water supply gets replenished through rainfall, the hydrological cycle. Now, all of this fresh water compared to the Earth's water overall is very small, a little less than 3%. So as we're seeing more and more places seeing less rain, more drought, what can they do to expand their water supply? Well, the reason I think desalination is going to be more important in the future is because desalination allows us to tap into the ocean and expand our fresh water supply. I'm not saying that it's going to be the tool everywhere. It's not going to be a silver bullet, but when it doesn't rain, we can desalinate. And where it makes sense, we should use this tool. The state-of-the-art method for desalination is reverse osmosis, or RO. 50 years ago, the dominant methods were thermal desalination technologies, basically evaporating water. But reverse osmosis has gotten a lot better and a lot cheaper over the decades, and is now the dominant desalination technology. What's pictured here is Carlsbad desalination plant. That's the biggest desalination plant biggest seawater desalination plant in the United States. Here you can see there are racks and racks of pressure vessels that are holding those reverse osmosis membranes that filter out fresh water. So RO has done a lot better, but there's still room to improve. So what are researchers looking at to improve this technology? Well, the first is energy consumption. If you look at seawater RO, and it requires really high pressures, it varies by plant, but roughly speaking, 1/3 of the cost of seawater RO is attributed to the energy cost. In brackish water desalination, brine disposal is the main concern. These desalination plants are usually located inland, so far away from the coast. They're desalinating brackish groundwater, and those desalination plants are producing a brine that they have to figure out some way to manage. So here, one way you can do it is with evaporation ponds. So dig a big hole, dump that brine in, and wait for it to evaporate. Another method is deep injection wells. So dig a really deep hole and put that water into the ground. These methods are really expensive compared to reverse osmosis. So if you were able to, people would much prefer to run RO at higher recovery and recover more water, produce less brine, and avoid digging these evaporation ponds. problem though, what's stopping us from doing that is that membrane clog. So this is an RO membrane. You can see each of these leaves is the membrane. That's what filters out the fresh water. And the way that these membranes are used in desalination plants is we take like 20 of these envelopes, 20, 40 of these envelopes, and roll them up into a spiral-wound membrane, basically into a tube. Basically, the problem is these membranes clog. The technical term is fouling and scaling. So those are three of the broad challenges that researchers are working on. So next, I'll talk about the motivation for this work, an introduction to reverse osmosis, and then talking about batch reverse osmosis as an improvement to RO. But before understanding RO, let's first talk about osmosis. So osmosis can be actually a pretty useful phenomenon to use in the kitchen, for example. So you can use salt. I mean, people have been using salt to cure things for ages, whether it's curing fish, curing meat. You can cure egg yolks by putting them into a bed of salt and letting them sit there. Basically what happens is the yolk, the salt draws moisture out of the yolk, and the yolk gets cured. So we're going to show that water is going to come out of the yolk using the water flux equation. So J is the water flow, and J is proportional to this term on the right, which is the driving force. We're going to look at the egg yolk and the salt. And when we think about these deltas, so delta delta refers to the difference across the boundary. We're referring to the difference between the yolk and the salt. So P is hydraulic pressure. So the pressure of the yolk minus the pressure of the salt. Both the yolk and the salt are sitting at atmospheric pressure, so the difference is 0. Pi is osmotic pressure, and we call it a pressure, but it's not really a pressure. It's a property of the fluid or material. And basically, the saltier your fluid or material, the higher the osmotic pressure. The salt obviously is really salty, so the osmotic pressure is going to be high. But the yolk, in comparison, does not have any salt really. So that term is going to go to 0, and we're left with negative pi f. If you plug those into the water flux equation, delta P equals 0, delta pi equals negative f, we find that the water flux is positive, and water is going to flow from the yolk to the salt, as we know. So the natural tendency is for water to flow from a not salty substance to a salty substance. That might be useful in the kitchen, but it's not useful for producing fresh water. So we need to think about reverse osmosis. So here, what we're showing here, this is a salty solution on one side, pure water solution on the other side, and in the middle we've got a reverse osmosis membrane. Now RO membranes are semi-permeable. What that means is that they allow water particles to pass through, but salt particles are not able to pass through. So here, delta P is 0 across the membrane. So the natural tendency is for pure water to flow across that membrane into the salty solution, and that's what happens. So if instead we want to produce fresh water, what we have to do is apply a pressure to the feed, that salty feed water, that's greater than the osmotic pressure difference. And what that does is that reverses the flow, and we end up producing permeate water, and that level here is going to increase. And because that pure water passed through the membrane, we call that permeate because it permeated through. So regular RO is a continuous process. What does that mean? Well, on the bottom here, this is a conceptual diagram of what RO looks like in that Carlsbad desalination plant, for example. So it's a continuous process, so that means that we have salty feed water that's continuously flowing into the system. This pump is pumping it up to a high pressure, so it can overcome the osmotic pressure, and that is entering the membrane module. That's that spiral wound membrane that we saw earlier, but all wrapped up. Now, as we move along the membrane module, delta P is greater than delta pi, so permeate is always being produced, and is permeating through that membrane. And as that happens, the feed gradually gets more and more concentrated, and we end up with a brine solution that continuously flows out of the system. You can see here the osmotic pressure starts out low as that feed enters. As the feed gets more and more concentrated, the osmotic pressure rises. And the way these things work, the pressure that this pump applies, that continuous RO pressure, must be greater than the osmotic pressure at the end of the system. So that's what it looks like there. And the problem here is continuous RO wastes a lot of energy because of this configuration. You can see the difference between the pressure and the osmotic pressure is very small at the end of the system, but at the front of the system is very large. The system's over-pressurized, so it's actually wasting a lot of energy that could be used more efficiently. So that's the whole idea behind batch RO, is to try to recover some of this wasted energy. And the way we do that is we don't mess around with the membranes. We're not material scientists, but we're really process engineers. So we design the process. So what we do is we turn this process from a continuous one into a batch process. And this is what it looks like here. So instead of having water flow continuously in and continuously out, we're taking a fixed volume of water, and that feed that flows out, we actually recirculate. And what that allows us, or what that changes, is the osmotic pressure is still increasing over the course of our process, but now it's increasing over time instead of across the distance of the membrane module. Since the osmotic pressure is varying over time, with this pump, we can also vary the pressure over time. And we can vary that pressure over time in order to track the osmotic pressure, just like that. And what this gets us is a big energy saving. And in fact, batch RO is the most energy efficient RO process possible in theory. So this idea has been around for a while, but there's been a lot more work on it recently over the past 8 years or so. And the reason for that is there were lower hanging fruit before this process redesign. Improving the pumps and the membranes and energy recovery devices got you a lot of energy savings, and you didn't have to worry about reconfiguring the whole process. But now people are looking at batch RO. So first, researchers in our group and in other groups wrote energy models to predict the energy consumption of batch RO. They basically found that batch RO is the most energy efficient RO process, more efficient than two-stage RO, more efficient than semi-batch or closed circuit RO. This research group in the UK built the first batch RO prototype, and they used a piston for their system, for their design. The same group looked at salt retention in batch RO. We'll talk a lot about this later. Jay from our group looked at the optimal design of batch RO systems, varying reset times and per pass recoveries. David and Emily and others in our group looked at the scaling resistance in batch RO. The idea that by rapidly cycling salinity, batch RO is going to be resistant to scaling, so we can operate at higher recoveries than regular RO. And finally, more recently, groups have thought about new designs for batch RO. This one here is a hybrid semi-batch batch RO system that reduces the footprint of the batch RO systems at high recoveries. So when I first started working on this 4 years ago, what was sort of missing was students in our group had invented a new batch RO design. Here there is a bladder. That bladder basically replaces the piston that we saw in the earlier slide. And the thinking was that this design is more advantageous because with the bladder, it's probably easier to manufacture and less chance for leaking. And you don't, with the piston, that piston during the batch RO cycle is going to be moving back and forth. Whereas this bladder is kind of freestanding and not touching any of the walls of the pressure vessel, and it's maybe just easier not to have to deal with that at all. So this is what we thought to build that batch RO system with a bladder, and this is what that system looks like. So you've got the bladder sitting in a pressure vessel, we've got our RO membrane, and a high pressure pump and our circulation pump. So when we want to produce permeate water, what we do is we take a makeup fluid and we pump it through that high pressure pump and pump it into the bladder. And that bladder wants to grow, but one thing to take note of is that water is incompressible. What that means is if you are pumping water into a tank that's filled with water, the pressure is going to rapidly increase. If you continue pumping water into that full container, the pressure, either the pump's going to break or the tank is going to break. Or in our case, we have kind of a safety pressure release valve in the form of the RO membrane. Because once that pressure in the pressure vessel exceeds the osmotic pressure of the fluid of that feed fluid in the pressure vessel, permeate is going to leave through the RO membrane. So in this manner, permeate is going to be produced at the same rate that makeup fluid is entering our high pressure pump. And all throughout, this circulation pump is circulating water around the system to keep the feed well mixed and to provide a cross flow against the RO membrane to reduce concentration polarization. We continue producing permeate water until the bladder is fully filled up. That circulation loop is now going to have much less water, but basically all of the salt. The salt can't pass through the RO membrane. So if we want to continue producing permeate, we can't do it like this. What we have to do is reset the system, and we start by flushing the system. So we open and close some valves, and the circulation pump brings in new feed, and it ejects the brine. We do that until all the brine has exited the system. Next, we need to recharge the system. We open and close some more valves. The circulation pump continues to bring in more feed, and now it's emptying the bladder. And once that bladder is completely empty and the pressure vessel is filled with feed, we can go back to the permeate production phase and do it all over again. So this is what that system looks like in real life. We've got the pressure vessel in silver down here. The bladder sits in there like that. The RO membrane there. We've got the high pressure pump. We've got the circulation pump. And we got controls and sensing. Now, we got the system up and running, and really the importance of this is the first batch arrow system with a bladder that has been built and operated. As far as I know, the only one. What's important here is the bladder. This is a new component that RO systems don't currently use. So people are rightly concerned about the reliability of this bladder. This bladder is growing and shrinking throughout each cycle. Can it do that reliably for thousands, tens of thousands, hundreds of thousands of cycles? If that bladder isn't able to do that, then the design isn't going to work. Well, our bladder is able to function. We've got it functioning for hundreds of cycles without failure. We haven't been able to do longer-term testing, but I think we've shown that this design can work and merits further exploration. The second thing we did with this prototype was validate energy models. We measured the energy consumption of the prototype. On the y-axis here, we've got energy consumption versus recovery ratio at various feed salinities and fluxes, and the measurements agree with the model. The importance here is now we can use these validated models. These models haven't been validated before to predict the energy consumption of batch arrow in seawater conditions. Because at the moment, there are no batch arrow systems that can operate at the higher pressures needed for seawater. This prototype and the UK prototype both are low pressure prototypes and can only desalinate brackish water. So we've demonstrated batch RO, we've validated energy models. So we're thinking we've got the most energy efficient RO process, so we're good to go. But with any new technology, things don't work out the way in real life that you maybe expect on paper. Usually you'll have practical losses or parasitic losses that come up. Maybe you didn't expect them before, or maybe you just aren't able to measure how much they affect your performance without actually building and operating the prototype. So that's what we did next with the prototype, is took a look at these practical losses, and then after quantifying them, came back and revisited to see really how much energy is batch RO going to save. The first practical loss is cycle downtime. So here we've got permeate flux. These are experimental measurements over time throughout the batch cycle. During the permeate production phase, we're producing water, but then during the fluxion and the recharge phases, we're not producing water. And that's the practical loss. If you take an average over the entire cycle, your flux is lower than your operating flux during the permeate production phase. A quick word on units. Permeate flux is defined as the permeate flow rate per unit membrane area. The units are liters per hour per meter squared. The desalination industry has developed this shorthand LMH, which basically means these units. So 15 LMH means that you're producing 15 liters per hour of fresh water per square meter of membrane area. The next loss is salt retention. So this is the reason we get salt retention in these systems. Basically, in any fluid channel, the fluid at the middle of the system, in the middle of the channel, is going to flow faster than the fluid towards the walls of the channel because the wall is the friction. What this means is you're going to get this region where there's mixing between the feed and the brine. So when you flush the system, you're actually going to have some brine remaining in the system when you cut off that flush cycle, rather than perfectly pushing all that brine out as you'd like to. What that means is the feed in the next cycle is going to be saltier than you expect it to because it's mixed up with some of that brine. Why do we care about the feed salinity? Well, this feed, 35 grams per kilogram, that's typical for seawater. What that means is you have 35 grams of salt per kilogram of seawater. Remember, feed salinity determines osmotic pressure. So the osmotic pressure of the feed is going to be 28 bar or 28 atmospheres. And if you increase the feed salinity, you're going to have a higher osmotic pressure, like that brine. So if we get a saltier feed in our system, that's going to push the pressures up, and that's going to push the energy consumption up. Here's another photo of our batch arrow prototype. Take a moment and yeah, see if you notice anything kind of interesting here. So we've rigged up this permeate tube, and it's going up really high, actually. So why would we do this? Well, we didn't do this to start, but through operating the system, we came across water loss and realized that this is something that we had to do in order to protect the membrane and also make running experiments easier. So basically, during the water production phase, remember we've got our RM membrane here. We're producing fresh water. That fresh water is flowing out of the membrane into this tube and traveling all the way up here and then dripping into our permeate collection tub. Now we noticed whenever we stopped the permeate production phase and went to the flush phase, water would start going down, and it would start from the apex and start to travel down this tube. And if you let it go long enough, sometimes it would actually re-enter the pressure vessel and bring air bubbles into that membrane. So that's the reason we brought this tube all the way up there. We wanted to give the permeate, give it more length to prevent that from happening. But this is the third practical law that we're thinking about. So this is what this looks like. This is experimental data. You can see here we've got the permeate production, and then here on that previous graph we showed zero permeate flux, but in fact there's negative permeate flux during the flush and the recharge phases. The way we measured this is with two flow meters back to back, one flow meter to measure the permeate production and the other flow meter to measure the water loss. The recovery ratio during permeate production was 50%, but we lost 2% of the water during the flush and the recharge phases. So the effective recovery ratio is only 48%. Remember, the reason this is happening is because of that egg yolk. We're releasing the pressure in that system, so the driving force flips, and we get osmosis, a natural tendency for water to travel back into a salty solution. So why do we care about these practical losses? When we're thinking about comparing batch RO to continuous RO, we want to make sure that we're making a fair comparison, apples to apples. So these are the typical seawater conditions of a continuous RO plant. The energy consumption is 2.2 kilowatt hours per meter cubed, so 2.2 kilowatt hours of energy per meter cubed of permeate. If we've got a batch RO system, and we're comparing it to the continuous RO system, we want to make sure that the same water is coming into the system and we're producing the same water out. We want all of these parameters to be the same. But because of these losses, the batch RO system is going to see a different feed salinity or operate at a higher flux or a higher recovery ratio. So we need to account for these losses in order to calculate that energy consumption with our energy models and then compare it to continuous RO. So for the cycle downtime, it's easy to calculate. It's just a proportion of the downtime to the cycle time. So the batch RO system will operate at a flux of 19 LMH in this example. With salt retention, we know the feed salinity is going to be greater. The question is how much greater. So we took the prototype and we measured the feed salinity elevation. What we did is we ran the batch RO system for multiple cycles using the same parameters And we measured the feed salinity between each cycle. The feed salinity started out low, maybe at 2 grams per kilogram, and with each cycle, it started to increase. But then eventually it reached a steady state. And once it reached that steady state feed salinity, we recorded that value and then moved on to the next measurement. So we're seeing that feed salinity elevation here. On the y-axis, as you move up, you get saltier feed, more elevation. On the x-axis, a longer flush. So the longer you flush the system, the less elevation you get. That makes total sense. What we've done here is we've non-dimensionalized these quantities. So we've taken the feed salinity elevation, which is the quantity that we are interested in, and we normalize it. We just divide it by this quantity here. This characterizes the degree of mixing between the brine and the feed. We do the same for the flush phase. So we've got the duration of the flush phase in the numerator, and we normalize that by the duration of the flush phase according to plug flow. Now, what do I mean there? So plug flow would be the ideal and not realistic case of the feed perfectly ejecting the brine. If T star is less than 1, we're under flushing the system, and basically that feed is not exiting the system. T star is equal to 1, that feed is traveling all the way to the exiting the system perfectly and ejecting all the brine. T star greater than 1, we're over flushing the system, and some of that feed is actually exiting the system. The reason to non-dimensionalize these quantities is because we can now plot our measurements all on the same plot regardless of what the feed salinity is. So all these black dots for tests run at 2 grams per kilogram, but these white markers are run at 3 or 4 grams per kilogram feed, but they fit on the same along the same curve because we've non-dimensionalized these quantities. So we aren't able to right now, but I'd expect if we ran a seawater batch arrow system, basically 10 times greater in salinity, those same results would sit basically in the same vicinity. So next, we calculated the feed salinity elevation according to ideal plug flow. So that's shown in this dotted curve here. Remember, plug flow is unrealistic. This can't happen in real life, but this is still useful to verify some of our findings. And the curious thing you'll find is that our measurements actually coincide with that curve at these low values of T star, less than this parameter I'm introducing here, T star E, E for exit. So basically what's happening here, remember in real life what we get is Taylor dispersion, where that fluid in the middle of the channel is traveling faster than the fluid on the channel walls. T star is less than T star exit, that feed is not making it out of the system. So if you just looked at what was coming into the system and what's coming out of the system, you wouldn't know the difference if you had Taylor dispersion in here, or if for some reason you miraculously had ideal plug flow. So at these low values of T star, that's why these two curves coincide. So that checks out. When T star equals T exit, the feed, that feed at the middle of the channel starts to make it out of the system, and you can see these curves start to diverge. And then finally, for T star greater than T exit, more and more feed is coming out, and the curves diverge more and more. Now, the other thing that's pretty cool is, according to the theory of Taylor dispersion, we expect T star to equal 2/3, which is pretty close to the T star that we measured. And that value of 2/3 is the reciprocal of that 3/2. Next, we calculated the feed salinity elevation due to Taylor dispersion. We can do that. It's pretty straightforward. So that's that blue curve here. And cool to see that it actually lies pretty close to our measured curve. So basically, what that tells us, so I'm highlighting this region here because I expect most batch row systems to operate at a dimensional of flush time close to 1 because you don't want to throw away too much pre-treated feed or leave too much brine in your system. So everything up to the blue curve is feed salinity elevation due to Taylor dispersion. So that's explained by that, remember, that fluid traveling faster. This difference, though, can be explained, part of it at least, by piping, the dead leg. So this is getting really nitty gritty, but basically, if you have the flush path going like this, a dead leg is where there's fluid in that pipe that's not getting flushed out of the system. So it remains in the system for the next batch row cycle and further increases the feed salinity. We didn't optimize our system to reduce these dead legs. Future systems probably will, but even if they spend a lot of time and effort doing that and got rid of all of this feed salinity elevation, they would still be stuck with the elevation due to Taylor dispersion. So here, I calculated the feed salinity elevation due to Taylor dispersion. So that's the minimum salt retention penalty at various recovery ratios and for various flush times. And these are those values for T-star equal to 1. So I think this should be really helpful to people working on batch arrows because it's a simple way to calculate what your salt retention penalty is going to be. For seawater, you're going to go from roughly 35 grams per kilogram to 38 grams per kilogram, 10% increase. Next, water loss. Remember, because you lose water during the reset phases, you're going to have to operate at a higher recovery ratio. In order to model this water loss, you can see it's clearly a transient phenomenon. So it's going to require transient two-dimensional equations, actually. So here is the equation that I solved using a finite volume solver. I adapted this model by these researchers in Israel and made these additions to the model. I'm going to draw attention to the Taylor dispersion and the recharge phase, because we'll see that on the next slide. During the flush phase, you've got feed that's entering the membrane channel here. So you've got a fluid velocity, or horizontal velocity component. During the recharge phase in our system, that velocity component disappears. So during the recharge phase, U goes to 0. And we'll see that in the results here. So here, this is that same membrane channel that we're seeing here. Feed inlet, feed outlet, membrane surface at the bottom. Red is the maximum concentration. Blue is the minimum concentration. And this is half the membrane channel because it's symmetrical, so we don't simulate the other half. And we start out with a concentration polarization layer. This is what you get in regular reverse osmosis. The first 5 seconds are going to move more slowly, and then after t equals 5 seconds, things are going to speed up because we're going to have this concentration polarization layer, and when the flush phase starts, a dilution layer quickly forms on that membrane surface as water enters the membrane. So now we're in the flush phase. Now we see fresh feed entering the membrane. That was Taylor dispersion right there. And now we're entering the recharge phase. That dilution layer now is diffusing upwards away from the membrane because there's no longer a flow velocity, a horizontal flow component washing it away. Yes, I'll just play it again. So Taylor dispersion here, and then the recharge phase. So we compared the model to experiments, and the results agree pretty well. I'm pretty proud that the model captures these three components. During the first 20 seconds, you get a rapid rise. That's due to that dilution layer, and then also ICP. The second portion is fresh feed coming into the system, scalar dispersion, and then all throughout the cycle, the permeate salinity is increasing throughout, which gives you this slight increase. The model agrees with the experiments pretty well across all of our measurements, 15 measurements here. The error was generally less than 20%, and especially if we exclude the recharge phase and only consider the flush phase, which you would see in a double-acting system, which is probably going to be the preferred design. That error drops down to 10% or less. So with this model, we're able to calculate what is that recovery ratio that your batch air system is going to have to operate at in order to achieve that 50% recovery. So we can take all of this together and now make a revised estimate of how much energy batch air is going to save. And here you can see the energy savings are going down from originally 22% without any of these losses down to 7%. Mostly due to salt retention and water loss. Now, salt retention, I don't think you can really get around, but water loss is something that we can maybe design around. So that's the next thing we'll be talking about. I shared these results with the group a couple months back, and then came into the lab, talked to Andrew, discussed some of the ideas I had, which were, none of them were that great. But then we came up with this improved design. So as your system has more cycle downtime, you're going to see more water loss. That makes a lot of sense. So the natural strategy is let's decrease the cycle downtime, and then we'll have less water loss. The problem is that membrane is the bottleneck. So on the right here, I've just unwrapped the system, make it a little bit more simple. These membranes have a maximum feed flow rate. So you can only flush them at about 4.4 liters per second. The membrane manufacturers don't recommend you go above that, otherwise you might damage them. So this results in a cycle downtime of 10%. The way to get around this is to branch out. So take that membrane, which is the bottleneck, and put it in one branch, and then take the rest of the system and put it in another branch. So that membrane branch, you can still only flush at that 4.4 liters per second, but now there's a much smaller volume there, so that flush time goes down to 7 seconds. Now the main branch has a bigger volume than the membrane branch, but you can flush it much faster now. Here, almost double the flow rate, basically to match the flush time of the membrane branch. So the cycle downtime goes down to 4%. This reduces the water loss by quite a bit. So you've got the double-acting systems and dotted lines corresponding rapid flush systems and solid lines. We're roughly reducing the cycle downtime and the water loss by half. So here you can see this batch air system can operate only at 53% instead of 57% to achieve that 50% recovery ratio. So what does this do for our energy savings? Well, it nearly doubles them. So we're going from 7% to 12%. We still have some water loss, and actually it is possible to get that water loss down further. But what I'm showing here, these batch air systems have got 4 membrane elements. Now you can improve the energetic performance of these systems by going to shorter membrane trains, so maybe going to 2 elements or 1 element. But as you get systems with less and less elements, you need more and more pressure vessels to hold the same membrane area. So I think the really short systems are probably not going to be practical. Something maybe closer to 4 might be the case, but that's just my thinking. So batch RO can save a decent amount of energy, but will make desalination more affordable. Finally, wrapping everything up with a techno-economic analysis. So that means techno means looking at the performance of our technology, and now we can do that. We can do a good job of that now that we have a good handle on what all these practical losses are. So now we're going to take all of that and integrate it with the economics of water desalination. So first, using batch RO to consume less energy. So going from 2.2 kilowatt hours per meter cubed to 2.0, 10% energy savings. With these systems, I'm using 6 elements in the membrane trains. Again, thinking maybe this is more practical. You've got less pressure vessels, so maybe less costly. The energy savings for a 100,000 cubic meter per day plant. This is a pretty big plant. At 10 cents per kilowatt hour, come out to $700,000 in energy savings per year. So this sounds pretty good, sounds pretty great, but one thing to know is that batch RO systems are going to cost more than regular RO plants. That's because batch RO plants are going to have more piping, they're going to have valves that regular RO plants don't have, and they're going to have more pressure vessels. So you can see all this equipment costs money to make, takes up space, so that's going to increase the cost of the plant. We estimate that increase is going to be 10%, so that 100,000 cubic meter per day plant, $120 million, tack on $12 million to implement batch RO, and suddenly that $0.7 million is not looking so big. Now, the energy savings you get do vary with the price of electricity. So if energy is more expensive, your energy savings increase. This looks more attractive. But on the flip side, if energy is really cheap, then it's not looking so appealing after all. But what if we use batch RO to produce more water? So instead of operating at the same flux and using less energy, what if we kept the energy consumption constant and increased the flux? Basically what we're doing here, remember that cycle downtime penalty was really small? We're taking advantage of that here and essentially operating at a higher flux intentionally, using the energy efficiency of batch RO, and actually getting something useful of that energy bump, as opposed to salt retention and water loss, where those are just parasitic losses. But why doesn't a regular RO plant do this? Well, that has to do with the flux distribution within that membrane train. So we've got flux on the y-axis and basically position along the x-axis. The flux is really high at the beginning of the system and gets really low at the end of the system, while the average flux is 15. The problem is the flux in the first element is greater than the maximum recommended flux. Membrane manufacturers set these guidelines because you're probably going to see more membrane fouling if you exceed this limit. With batch RO, you get a more even flux distribution, so you can achieve the same average flux, but this is what that distribution looks like. So you're seeing 25 LMH at the front of the system, much less than that 32 LMH limit, and much less than what you're seeing in regular RO systems. So with this graph here, I'm plotting peak flux, so that's the flux at the front of the system, 39 and 25 versus average flux. With batch RO, we can increase the flux from 15 to 20 LMH, and here we are exceeding the membrane manufacturer guidelines by a bit, but we're still staying below the peak flux of a regular RO system. So maybe we don't increase flux quite that much, but in principle, we can produce more water with the same membrane area while still without compromising membrane life. So we do that here to increase the capacity of the plant. We've got a membrane area of same membrane area, but increasing the flux from 15 to 20 LMH and increasing that plant capacity by 30%. So what does that mean for us? Well, first, with all of that extra water, we can sell that and get more money. So the plant gets an additional $8 million in revenue. You do have more energy costs to produce all that water. That's an additional $2.3 million in energy costs. The net benefit is $6 million per year. And this is 10 times greater than that $0.7 million per year we're looking at by reducing energy. However, though, with increasing the plant capacity, you do have to increase CapEx by a bit more. I estimate 20% to implement both batch RO and to account for your increased feed and brine flows. But still, compared to that $6 million, it's looking pretty good. And the cool thing is this net benefit is actually independent of the electricity price. So no matter whether electricity is 40 cents per kilowatt hour or 2 cents per kilowatt hour, you're going to be saving you're going to be gaining $6 million per year. So can batch RO make desalination more affordable? To look at that, we need to take a look at the levelized cost of water. Calculate that, we take the total cost, so that's CapEx, OpEx, energy, labor, and divide by total water production. With the regular RO system we're looking at here, 80 cents per meter cubed of fresh water. When we use batch RO to reduce the energy, we reduce energy, but we actually see an increase in the cost of water. Why is that? We're looking at the numerator and we're reducing the energy, but CapEx is going up and basically overrides that savings. By producing more water, though, we can actually produce more water and cheaper. So energy and CapEx costs are going up, so the numerator is increasing, but the denominator, that total water production, is increasing at a greater proportion. So the overall cost of water is going down. Here by 5 cents or 6%. That might not sound like a lot, but cost of water is the main metric that matters when it comes down to, you have hundreds of millions of dollar contracts being decided by the cost of water. If you can shave off a couple cents here or there, that is a really big deal. So, almost there. First, I'm going to lay out the major accomplishments of my thesis. When we first started, only one batch RO prototype system had been built. I demonstrated the first batch RO system with a bladder. This work shows that the bladder design works. Next, I used experimental measurements from the prototype to validate, for the first time, energy models of batch RO energy. I quantified the minimum salt retention penalty for any batch RO system. This is important because, as far as I can tell, there's no practical way to avoid this penalty. So it must be properly accounted for. I developed the first model for water loss in batch RO and performed the first full accounting of all 3 practical losses. The combined effects of salt retention and water loss are pretty bad in seawater RO. But if you branch out, you can rapidly flush the system and cut water loss in about half. I thought that batch RO would be useful for reducing energy, but have now realized that it's more valuable to use its energy efficiency to produce more water cheaper. Here's a list of my journal, papers, comments, presentations, and patents. Quick aside, I'd recommend any graduate student try to go to a conference early on. I've learned so much from going to these conferences and talking to people, stuff I wouldn't learn in the lab. Definitely influences my research. And you also don't really understand your research until you've presented it to others, as I've discovered over the past week or so. Plus, conferences are a lot of fun. But back to the original question. Can batch oil make desalination more affordable and sustainable? As I've shown you or argued today, batch oil can make desalination more affordable. Until just last week, I was stuck on this idea of batch oil being more sustainable because of its energy efficiency. And I was trying really hard to find a way to make it work. But I think for a while now, I've known what I think I'm only saying now. Electricity is getting cheaper and cheaper, and hopefully by 2050, we can decarbonize the grid. So I think, yeah, the value of batch oil is not in reducing energy consumption, but I still think batch oil can make desalination more affordable, more sustainable, by reducing the carbon footprint of the plant itself, basically getting the most out of all the equipment. So we'll see. That concludes the technical part of the program. I've got a bit of an afterword, if you'll bear with me. Working on a desalination startup, people often ask me why water, and I never had a great answer. It took me a long time to realize one of the reasons why. This is me back in 2010, before I came to MIT. Before I came to MIT, I took a gap year, spent 6 months living and teaching in rural Kenya. Way out on top of the mountain, really in the middle of nowhere. The village had just gotten electricity the year before I got there, and there was no running water. So I lived at this school that I was teaching at, and we had this cistern, and that was my water for those 5 months. Used that water for drinking water, used it for doing my laundry, for washing dishes, for cooking, for cleaning the house, for taking bucket showers. So, I mean, for most of the time, where I was living is the middle of the Rift Valley, so pretty green, as you can see there. But there was a dry month or two where I could see that the flow coming out of the cistern, which was really big, was getting lower and lower. So it was definitely on my mind that, this cistern, which provided so much for me, was running low, and I didn't know when it was going to rain next. It was definitely on my mind. I definitely was more careful with my water consumption. Conserved more water. And I was never in mortal danger. If worse came to worse, I'm sure someone would have brought me water, or I could have gone down to the town and bought some bottled water. But that would have been like a 5-hour round trip journey. So definitely really inconvenient. All that to say, I know what it's like to rely on rainwater entirely for your freshwater needs, and I guess I realized over the past couple months that that's probably part of the reason I joined Professor Leanhardt's group. And I don't even know if I talked with you, Professor, when we first spoke. So in 2015, I started grad school, joined Professor Leanhardt's group, and started working on reverse osmosis. I'm showing this picture here because this is a batch setup I inherited from Emily and Allie back in 2017, about 4 years ago. And everything I presented just now has been done in those last 4 years. I remember, yeah, the summer of 2017, I knew a little bit about reverse osmosis. I'd done theoretical studies of two-stage RO with Ronan, published a paper, gave a conference talk, but I had no practical desalination experience. This is the first desalination system this is the only desalination system I've operated. I really didn't know what I was doing. And honestly, for the first, I don't know how long, for a while, I was afraid to turn on the pump. Because I just didn't know what I was doing. And in retrospect, I almost certainly should have asked for more help, but that's definitely one of my flaws. But yeah, I was doing everything I could do to avoid turning on the pump. But I guess 2 points. One is, it's pretty amazing looking back how far you can go in 4 years and how much you can learn. And the second point is, don't be afraid to turn on the pump. So this is the end, coming to the end of my time as an MIT student, and it's been an amazing experience. The Mikey office asked us to submit our favorite memories, and there's no way I could pick a single one. So when it comes down to it, I love MIT for the community. It's just been incredible being able to learn and work and play with great people, and I'm really gonna miss my time here. So there are a lot of people to thank. I'll try and get through this quickly. Professor Lienhardt, my advisor. I feel really lucky to have you as an advisor. Professor Lienhardt has supported me through some challenging times, and I think he epitomizes what it means to be an MIT professor. MIT's motto is mens et manus. That's Latin for mind and hand. Mind, mens. Professor Lienhardt and his father's heat transfer textbook is available to download for free online for anybody. So I think that's all I need to say there. And Manus, what I look to, and the practical stuff is, he's had 2 successful desalination startups come out of his group, so his research has impact. So that's that. Amos, so I'm thanking my thesis committee right now. Amos, you always come to our committee meetings with really great feedback, really great ideas, and I really appreciate all the careful notes that you take. And I've definitely learned a lot from you, and I'm sure we'll continue doing so. Alan Myerson from chemical engineering, Professor Alan Myerson. I asked Alan to be on my committee back when I thought I was going to run experiments. I was planning to run experiments to study scaling in batch RO, and unfortunately wasn't able. I was probably overambitious, but also experiments got disrupted by COVID. But hopefully I will be able to get to that work at some point in the future. But I'll definitely take to heart one thing Alan said to me, and it's that if it were easy, someone would have done it already. And finally, Emily, on the right of this photo. It's really cool to have Emily on my committee because I talked to Emily. Emily was a student in Professor Linhart's group. We were students together. She was a couple years ahead of me. She actually spoke with me when I was a senior, looking at different groups. And then I inherited the bachelor setup from her. We wrote a paper together. And then even now, the past couple months, we applied for a grant together to study salinity or scaling resistance in batch RO. And particularly, Emily pushed me to further develop that water loss model. I'm really glad that you pushed me to do that, Emily. So thank you. In addition to my thesis committee, I've had lots of mentors over the years in all sorts of areas and fields. And I think all I'll say is, I think the best thing I can do to repay their support and inspiration and encouragement is to pay it forward. There are a lot of people to thank, 10 years at MIT, but I got to thinking and I realized most people that I'm close with, like the overwhelming majority, maybe 99%, are people who I've been on teams with. You get to know people really well when you're on a team together and working together. You get to know how people think. You need to learn how to work with them, despite, maybe you don't get along, but maybe you have differences. But yeah, I've loved all of these teams that I've been on. The other way, the best way to get to know people is probably by living with them. And I've had some incredible roommates. Fortunate to live with these people over the years. So it's definitely been an adjustment since last June. I've been living by myself at ADP, where I'm a graduate RA. I think definitely by the fall, I was getting to a dark, maybe not dark, but I don't know. It's getting pretty lonely, definitely, living in that big house by myself, and COVID was raging, so people were tightening their bubbles. But fortunately, this restaurant across the street from ADP, I got to know, started coming in, and Tracy was gracious enough to welcome me into her COVID bubble. And almost since then, I've kind of been living at Pazu. That's where I am right now, giving this defense. So thank you, Tracy. I couldn't ask for better friends. That's all I'll say. As some of you may know, my parents moved to Japan in 2013, and that's a bit far to travel to for Thanksgiving. So I just wanted to thank all of the families who opened up their homes to me for the holidays and throughout the year. I really appreciate it. And finally, my family. So there is Quark, Quasar, and Quantum, the famous three Qs. Quark is tuning in from Seattle. Quasar is tuning in from Tulsa. I haven't seen that. I haven't seen any of my family in over a year because of COVID. Really looking forward to seeing you guys soon. So this photo, just really quickly, Quasar went to the California Institute of the Arts. We were sitting on these steps, and these are my parents, Mama, Baba, taking this photo of us, and this is the behind the scenes of that photo. My mom, we disagree a lot, but I'll admit here for everyone to witness that you're usually right on the things that matter, and you definitely know me better than I know myself. I think sometime in grad school, my dad told me how he'd gone into MIT in Wisconsin for grad school for his PhD in solid state chemistry. People often like hear that my dad went to MIT or that he's a professor. He didn't go to MIT. He didn't end up going because he was not a U.S. citizen and didn't have the financial aid. I guess didn't have a fellowship that would allow him to go to MIT. Wisconsin was a better financial option. But yeah, my parents have definitely made a lot of sacrifices so that I could go to MIT and to do really whatever I want afterwards. So I'm incredibly grateful. I think I was in high school the first time my dad mentioned graduate school to me. I think he waited until college before he said you should get a PhD. So naturally, from that point on, I was dead set on not going to graduate school. But junior year of undergrad, I did some research at NASA Goddard, realized I kind of liked it, so I decided I might want to apply to graduate school. And then even when I started graduate school at MIT, I was telling myself, I'm not going to get a PhD, I'm only going to get a master's, 2 years and I'm going to get a job. But here we are. So I'd like to dedicate this thesis defense to my dad for teaching me the most important lesson of all, how to treat people. And with that, I will take any questions people have. Thanks for listening.
Thank you, Quantum. Thank you very much. We will proceed as follows. We have time now for questions from the broader audience. We'll take those questions, and after that, the thesis committee and Quantum and any MIT faculty will proceed to a breakout room where the committee will question him. Then we'll kick Quantum out back to the main room, and we'll deliberate and come back and report. So if you'd like to ask a question, I suggest that you raise your hand with a little feature under participants. There's a hand raise. And Quantum, can you see the hands that are raised?
Sorry, I don't have, give me a sec.
Okay.
Yeah. Yeah, Quark's got a question.
So first off, congratulations and good job on the presentation. I think going in, like I didn't really know much about reverse osmosis coming in, and I feel like I learned a lot. I have maybe 2 or 3 questions. I'll probably cut it to 2. The first is, have you experimented with changing the size or shape of the bladder? And the other one is it possible to use some kind of agent chemical to precipitate the salt out to effectively reduce the osmotic pressure?
Okay, so the first question, changing the size or shape of the bladder. We've changed the size of the bladder. So we've worked with smaller and larger bladders, definitely. And it doesn't really change the operating principles. It just changes kind of what limits you can operate the system to. Shape of the bladder, we haven't looked at that much. Maybe we've changed the end caps of the bladder to be spheres versus flat. Yeah, and that actually does affect how well the bladder empties out. So the hemisphere at the end of the bladder is actually better than a flat cap. but I think that's the extent of it. You're kind of restricted because the pressure vessel is just a long cylinder, so you don't have much to work with, really. And the second question, you said precipitating. Can you repeat the question quickly?
Yeah, so is it possible to precipitate the salt? Like I know in other ways of water extraction, like heavier contaminants are precipitated out, but maybe salt's like too small to do that.
Yeah, you can definitely do that. I think IDE is a desalination technology company. They do exactly that, where they precipitate the salt out. Yeah, in order to reduce the salinity or the osmotic pressure. Yeah, good question. I see David's hand up.
Really nice job, Quantum. Very great models.
Thank you.
I had a question about commercialization potential and particularly around what is the commercialization path forward and what system sizes and different salinity ranges are the most promising.
Okay, you cut out a little bit, but I heard you asking for commercialization path and then what sizes and salinity ranges for that commercialization path. So I've got 3 ideas. The first is less brine in brackish water RO. So these are the annual savings you would get for brine disposal, depending on the disposal cost and how much you're able to reduce the brine from an initial recovery ratio of 80%. So I think batch RO should be used as a brine concentrator. So 1,000 cubic meter per day brine concentrator gets you to that 90% recovery and costs about $2 to $3 million. So it's probably only the biggest factor here is how much the brine disposal costs, which makes sense. The second beachhead market is retrofitting old seawater RO plants. So for like state-of-the-art seawater desal, you save 10% energy, but if you got an old plant with really inefficient pumps and energy recovery devices, doing a retrofit might make sense. So this is again for 1,000 cubic meter per day plant, but now you're retrofitting it. Retrofit costs maybe 10 to 20% of the overall plant cost, 250 to 500,000. So the main factor here is what was the original specific energy consumption? How inefficient are you starting with? And what is the electricity price? Finally, producing more water for off-grid RO. So this is simulating solar energy throughout the day. Batch RO can make use of more of that peak and produce more water during the day. And this is preferable because you can reduce the batteries that you use in design, and water tanks are cheaper than batteries. And you're getting to this peak by operating at a higher flux. And it's actually, I was working on this last week, and working on this is what made me realize that why not operate at a higher flux for full-scale seawater desalination. So yeah, you never know what dots you might connect when you're doing research.
Great, thanks.
Are there further
Yeah.
questions? The raise hand feature is under the reaction button on the bottom right if you're having trouble finding it. All right, well, seeing no further questions from the audience, we will then proceed. The committee will move to the breakout room, and we'll come back and see you folks soon. And Quantum, do you have the breakout room ready to go?
Give me Give me a moment.
All righty.
Could any MIT faculty that want to be in the breakout room raise their hand so that I can locate you, please? I see Rohit. Yeah, I guess other than my thesis committee members. Okay, cool. So I've got the thesis committee plus Rohit. So okay, I think we're good to go.
Great.
See you guys soon. I need to put myself in the breakout room.
Good job, Quantum.
Thank you.
It was awesome.
Yeah, good talk.
Hey Cam. Hey Ivana. Hey Andrew.
How did the questioning go?
A little bit tough.
Looks like it went terribly from Quantum's face.
Thank you.
But you
Definitely
survived.
glad I survived, yeah. Professor Lienhardt didn't ask any questions. Did he ask you anything, Ivana?
No, he didn't ask
No.
anything. It was all the other
Okay.
committee members.
Okay, got it.
My brother's taking a final right now, so he's very upset that I'm speaking. Sorry, dude.
Oh dear. Hey everyone, we're back. Where's Quantum? Oh, there's Quantum. A gallery of faces. So congratulations, Dr. Wei.
Congratulations.
Thank you.
Great presentation. Everyone enjoyed it very much. By the way, you had
Thank you
almost
all.
100 people at one point, so.
Well, thank you everyone. Yeah, really appreciate everyone sticking around. Yeah.
So how are you going to spend your afternoon, Quantum?
Probably take a nap. I didn't get much sleep last night.
Right. All right. Well, that's a good
Yeah.
idea. Super duper.
Yeah.
All right, then I think I'll let you chat with the many friends you've got here. I thank the committee again for joining us today. And congratulations on a very successful dissertation.
Thank you, everyone. Thanks, Professor. Thanks, Amos. Thanks, Alan. Thanks, Emily. Thanks, Rohit.
Awesome job, Quantum. Congratulations.
Thank you. Hey, Kaylee.
Congrats, Doc.
Thank you.
How are you feeling, Q?
Good? Yeah, I don't know. Maybe I'm in shock. I don't know. Yeah. I can't believe
It was
it's
a really great
over.
presentation.
Well, it's not.
Really awesome.
Say again?
It was a really awesome presentation.
Thank you.
Yeah.
Yeah, Quantum, well done. Just wanted to log on and say, like, that was such a fantastic presentation. Like, you got me tearing up toward the end there, and it was really, your work's very impactful and very impressive work you've done.
Thanks, Sam. Where are you right now? Your room looks really nice.
I am in Denmark, actually. I've started my postdoc at DTU.
Oh, wow. Nice. Thanks for tuning in. I guess the timing's good for you.
Yeah, it worked out perfectly. It's nice. This is kind of an afternoon defense for me.
Hey Q, congrats, that was awesome.
Hey,
Didn't really
Sam.
understand any of it, but sandwiches and cocktails on me at Pagu.
Sounds good.
See you later.
See ya.
Are you doing anything special to celebrate?
Yes, I think.
Haven't planned
Definitely.
that. That's what happened to me.
I don't have anything planned, but yeah, I mean, if people, I mean, whoever's in Cambridge and wants to do something like in the later afternoon, I probably should. I really didn't sleep at all last night. I definitely should go take a nap. But did you sleep before your defense?
Like 5 hours.
Okay. That
Yeah.
sounds pretty good.
Yeah, take a break and then we can figure out how to celebrate.
Yeah.
Sweet. Sweet, sweet.
Quantum, good job.
Thanks, Tracy.
I listened to most of it, but I also became like a single mother of 3 children during that time. So
How three?
this is Tycho. Nina brought Tycho over. So
Oh, nice. And then left?
and then somehow everyone left, and I was like, all right, I guess I have 3 children to watch. Johnny told me I should ask some questions, but I decided to hold those off until later. I was like, I'll ask those privately.
Yeah, that's fair. Yeah.
But mostly because I'm like, how do we fix Cambridge water? But yeah, great presentation. It was nice to hear your stories about your experience in Kenya as well. One of my best friends did some teaching in Kenya for a few years. She's back in San Francisco now. But yeah, she used to like FaceTime me or send me photos and videos. And it just seems like very rural out there. So is that pretty much how you, I mean, that was your gap year, right? So that's how you, like, is that what motivated you to do your bachelor's and PhD?
No, well, I got into MIT during my senior year of high school, and they allow deferrals. So they like accepted but deferred for a year. Actually, half my gap year was in Taiwan. So half in Kenya, half in Taiwan. And I don't know, I don't think the Kenya experience was really top of mind, but yeah, I guess it was definitely within me that whole time.
But when did you specifically like want to do water RO and desalination?
I applied to grad school, got into MIT, didn't get in anywhere else, so stayed at MIT. And I wasn't looking for water desal, I was more looking for labs that were doing thermal fluids engineering, those were the subjects I liked during undergrad. And water desalination was the most appealing application.
Cool.
Yeah.
Great. Okay, well, I will see you soon. I hope.
Oh, Tracy said that.
Classic Zoom
We said
issues.
that for a sec.
All right, Quantum, I gotta drop off, but again, congratulations. Great job, dude.
Thanks, man. It'll be you pretty soon.
I see the light at the end of the tunnel. But it's like, it keeps feeling further and further away. Getting there. But getting there. All right, guys. See you later.
You'll get there. See ya.
Bye.
See ya.
Congratulations, Dr. Wei.
Thank you.
I have to get out of bed and make coffee so I can get to work.
What time is it now? Like,
it's like 7:30. No, it's almost 8. So, yeah, congratulations.
Thanks.
See ya.
See ya.
Yeah, great job.
Thank you.
Yeah, let me know if you want to hang out later.
Yeah, definitely. I'll text you. Cameron, are you free?
Yeah, I'm free whenever.
Okay, cool. Great.
I mean, I have
We'll figure
practice,
something
but if I can join before or after. But
When
you should have
practice?
5 to 7:30.
Okay. We'll figure something out.
Yeah, I mean, I can just join whenever.
Yeah.
All right. See ya.
Yeah.
Hey,
Lace.
Cameron. Hey, Mark. Hey, Bitsy.
Congrats.
Thanks.
Quantum, I want to extend
Thanks for coming,
congratulations to
Mark.
myself and Cal. I'll have to run off to class, but we were watching.
Yeah. Sweet. Love it.
I gotta drop 2Q.
Okay. Cool. Thanks for joining.
But I'll
Hugo.
call you later, all right?
Yeah. Yeah.
All right. See you, dude. Congrats again.
Thanks.
Congrats, doctor. I'm so proud of you. Yay.
You did it.
I know. I literally feel like I just got my PhD for the second time. Truly.
What's up, Bitsy?
Oh.
Gilbert.
Congrats, Q. 10 years, man. Way to go.
Man. Crazy.
Dr. Q. I just texted you. That's all I'm going to call you, Dr. Q.
Doesn't it sound like a member of the X-Men?
Well, I was thinking like Bond villain. Or like, but yeah, something like that. That's awesome. How intense was the follow-up, the questions from the faculty? It was pretty quick, no?
I don't even know. How long was I out for?
20, I don't know, about 20 minutes.
Okay. Well, Cameron McBride. He just went last Friday, and his was like, I don't know, like 5 minutes or less. It felt like, I don't know, 20 minutes of questioning. felt like kind of a long time. Yeah, I don't know. I guess not too long, but they were like pretty, kind of intense questions. But yeah.
That's cool. I mean, it might as well ask you like some tough questions. It was 6 years of hard work. So well done, man. Dr. Q, man, this is the first one I went to. It's awesome. That was really cool.
Yeah.
You should get some rest, dude. You deserve it. Well done.
Yeah, I will, definitely. I think the adrenaline will wear off like soon, and then I'll crash.
Yeah, get a bite to eat or something. Take a nap.
Yeah.
All right.
Good to see you, man.
Yeah.
Yeah.
Hopefully see you soon.
Hopefully see you soon. Yeah. I'm thinking of, yeah, I don't know if you're traveling at all, but we're thinking of going to Seattle in June for Diaz's birthday.
Oh shit, that'd be awesome.
Yeah.
We're going to Greece. In June, like the second half of June.
Yeah.
Planning a wedding. Details to come. But yeah.
Is the wedding gonna be in Greece?
Yeah.
Nice.
But it's like super early. Hey, that sounds awesome. Yeah, let me know. But in the second half, we're going to be in Greece. Yeah. Dude, congrats, man. Holy shit.
Thank you.
Mr. Doctor.
We were just talking, So and Haley they're briefly, I think, considering Italy versus upstate New York for their wedding. I think it's gonna be upstate New York, but I think Diaz and I were talking about how it'd be cool to have a destination wedding. So
yeah, for us, I mean, it's going to be like a destination wedding for me or Anna either way, because she's never lived in Dallas where her family is now, and our family's friends are all over. But yeah, that'd be fun. Hopefully people can make it. I gotta coordinate with so we like don't pick like the same weekend.
Yeah.
And then, well, yeah, hopefully see you soon. If I'm in DC next, I'll hit you up, or Boston or whatever. If Seattle doesn't
Yeah.
go.
Definitely.
Amen. I'll let you go. Congrats, man.
Cool. See you, man. Thank you.
Yeah.
There he is.
Nice job, Q. That's good.
Thank you. Yo, Cleena.
Oh, hello. Dr. Q. It's been done.
Dr. Q.
Congratulations.
Thank you. Diaz, are you at work?
I'm on my way in, but can't think of a better start to the morning. That was awesome.
Thank you.
Just immensely happy for you. It's so cool.
Yeah.
Very the timeline definitely had me reflecting.
What was that?
All the way back to freshman year. I remember when you showed the
Yeah.
picture of yourself in Kenya. I remember that was your profile picture when we found out we were gonna be roommates.
Yeah. Yeah.
I remember seeing that picture before I met you.
So awesome.
Good memories of that picture. That was fantastic, though.
That was such a good talk. It
was amazing.
That was
really incredible.
Great.
That was perfect.
Thank you. Different from what you guys saw.
Well,
it changed considerably.
Yeah, the process was good. It worked out really well. I thought it was really really accessible to people who might not know anything about reverse osmosis. So it's definitely not an easy thing to explain. So you did a great job there.
That was the idea.
And all the energy savings and so, you know.
So.
Did you work on it all night long?
I was doing so. Yeah, I guess basically. I was working up till like 5, and then I tried going to bed. I had an 8-hour alarm, so I was taking 3 hours of sleep, but like I went to bed and was just running through the presentation and would like think of something I wanted to change, and then like run over to my computer and do it. So like, I don't know, maybe did that like 6 times until it was 7 a.m. and then it was just light out. Like, I could just take it out.
I can't even imagine, Q. I lost a little bit of sleep over it. I was so excited. I woke up at 4:45. I was like, no, it's not time yet.
Queenie, did you spot the 2 course 2s?
Yeah, it was funny. My mom was and Dad were both on too.
Hey, I saw, yeah.
She called and said, 2 course 2s, incredible that Q put that on there. So yeah, that was great.
Was that for the 3D printer?
Yeah.
Oh, I love that.
That
I
was
didn't
a
realize you
fun
guys named
IAP.
yourselves.
That was super fun.
All right,
So fun.
I gotta
I
run,
still have
but
the printing.
congrats
Okay,
again, Q.
yes.
You still have it?
We'll chat later. I still have it.
That's great.
Yeah. I don't know. I mean, it's been like sophomore year was 2013. January 2013. 3D printers have gotten way better.
They've gotten so much better and so much cheaper too.
Yeah.
With the money we spent on that, we probably could have. Now we could buy a pretty nice one. But it's all about the experience.
Yeah.
It was never really about printing stuff. It was more about figuring it out together.
Yeah. Yeah. So I mean, the thing I was thinking. I mean, yeah, all this time I've had it. I was thinking like of trying to find like. At first, I was thinking of selling it, but then realized that was like silly. But like, I don't know if I could even give it away. But like, I don't know. If you found the right kid who wanted to like get that thing up and running again, that'd be you'd learn a lot.
Yeah, definitely. I wonder what all the software is like these days. If there's improved software, because there's always kind of you have to jump the file between multiple programs to get it to work. But yeah, you should definitely.
Wait a couple years, you can treat it like you're rebuilding an old car.
What was that, Abel?
Said if you wait a few more years, you could just treat it like you're rebuilding an old car.
Yeah.
It'd be vintage.
Wait until it's 10 years old. Wait a couple years.
Yeah, 10-year reunion. Rebuild it.
That's not a bad. Not a bad idea. Antique 3D printer.
Quantum, Marcel was very interested in all of everything you had to say.
Yeah.
We were asleep, but he was paying attention. All right.
Do you have
Well,
a foster right now?
we're gonna get one today. Another 75-pound pit bull. So named Angelo. So we'll see how it goes. Hopefully, we won't adopt him.
Cool. Well, is it work time for you?
Yeah, just about. I need to take the trash out. But once again, congratulations. Couldn't deserve it more. And I hope you have a wonderful first nap as a doctor. I heard their naps are fantastic once you're a doctor, so you're in for a treat.
Yeah.
And have a great rest of your day. And once again, fantastic work. So cool.
Thank you, man. I'll see you.
All right, well, I'll see you in a month.
Are you coming?
Yeah.
Nice. See.
Celebrate then. All right. See you, Q.
Love it. See ya.
Bye.
Anyone still there?
Yeah, I was just gonna say I gotta head out. So I'm taking Allison into work and then into the office. But
cool.
Good job today. It actually progressed quite a lot, like from since yesterday. I feel like the confidence there in the moment, game time, and all the little notes we talked about was really great.
Thanks to your comments, definitely. And I did another practice at 8 o'clock that evening and then made more improved. Yeah, I was working on it all night. So
that's great.
Are you guys coming to New York?
I'm 100% down. I'll convince Allison. We're going to Ohio this weekend, and then we go to New York next weekend. Yes. Looking good. We have to confirm she's not working, but if she is, I'll leave her.
Cool. Sounds good.
Congrats. Good job.
Thanks, Allison.
See you soon. I hope I get to see you soon.
Yeah, see you soon. Can't wait.
But yeah, we got to get going to take Marco out and stuff, and she has to work. But thanks for inviting us. It was great seeing you. Congrats. Sorry.
Yeah, for sure.
More than Diaz. Marco was also impressed by your speech. He loves a good clean water bowl. Alrighty, man. Take care.
See ya. Take care. Bert, you there?
Yeah, I'm just chilling. Yep.
Cool.
Just listening in.
Yeah.
What were you saying?
You want to hang tonight? What's going on with yours?
So I submitted my proposal, and then I have to defend it in 9 days next week.
Okay.
So yeah, so I've been working pretty hard, and I will be this week, but I could potentially hang tonight.
Okay.
Yep.
Cool. I'll let you know what's going on.
Cool. Yeah. Yep. But yeah, that was good. I finally think I understand what you're doing after all these years.
It's definitely the best I've explained it. So
yeah. I mean, a lot of the times I just don't understand something, on the first pass of hearing it. So I think just hearing it. Yeah. So.
Yeah.
Yeah. I think the first time I saw your stuff was your first committee meeting. Your slides for that. For some reason, you were showing those to us or something like that.
Yeah.
So
at a potluck.
I kind of saw. Yeah, it was a couple of years ago or something. And so it's I mean, overall, it hasn't changed that much, but you have results now, which is good. So.
Yep.
Cool though. Yeah. Congrats.
Thanks, man.
Yeah.
I'll let you get back to it.
Yeah. I mean, I've been just doing stuff the whole time. I just have you on your own monitor and then my other stuff on other monitors, but yeah. All right. Cool. Yeah. I'll see you around sometime. If not today, some other time in the next couple of weeks.
Yep. Yeah. Definitely.
All right. Yep.
Cool.
See ya. Yep.
Yep.
Congrats. Yep.
Thanks. Anyone else there? Victoria?
Hello.
Hey.
Yeah, good job on the presentation. Congratulations.
Thanks. Glad to be done.
Yeah.
I still have to do a little bit more work on the thesis, though. I have to write the last chapter. We'll kind of rewrite the last chapter. And then actually a lot of these figures from the defense, one of my committee members suggested, and it's a good idea to put it into the thesis. So yeah, there's some more work to do.
Yeah, well, I should get going.
Yeah. Thanks for taking the time off.
Yeah, it's not an issue.
Cool.
All right, guess I'll see you around.
Yeah, I'll see ya.
Bye.
Bye. Anyone there?
Kwana,
Yeah.
congratulations,
Thank you.
Dr. Kwana Moy. Huh?
Mm-hmm.
这个从大学1年级到现在是10年了
10
years.
Yep.
It's a long
Plus the
time.
summer. Yeah.
Maybe next Monday we can chat more。那个下一次那个 Zoom 的时候，Daddy 累了，妈咪也累了。
Yeah, go to bed. Yeah.
OK， 好了，Good night 了。好了，你也好好睡。Take a good sleep。妈咪问说有几个人 tune in， 你知不知道 ？Maybe 50.
Professor Linkard said close to 100.
Oh, okay. Yeah.
Yeah.
Okay. Congratulations.
Thank you.
Take a break. Take a good
Yeah.
rest. 好了，来，我们是晚上了。
Yeah. 晚安。Victoria, are you there? Okay, I'm going to end the Zoom. So thank you for joining, and